the last session for the first Vision Day. My name is Anne Wendel from VDMA Machine Vision, and it's my pleasure to moderate this session. It's always one of my favorite, if not the favorite session of the day. It's the Vision Startup Pitch session. So today we have 4 companies, newcomers from the field, exhibiting here at Vision. One of the 34 companies. Well, in total 34 companies. So these companies, they said, hey, I want to become the Vision Startup of the day. If not, the Vision Startup 2024. So with me already 3 of the 4 speakers for today. I say fingers crossed. May the best win. A very warm welcome also to the jury members sitting here, first and second row. So welcome, VDMA Machine Vision board members and friends. So a few years ago, they were in the same position as you. They founded their companies and they said, I'm going to have a great approach and I'm going to convince the rest of the community. So here we go. And I hand over to the first speaker, Spectricity. Henrik, you'll start with miniaturized multispectral imager.
Thank you. Hello. I am Henrik Andersen. I'm the Chief Marketing Officer in Spectricity. We're a company in Belgium, and we do miniaturized multispectral image sensors. Our solution captures the spectral signature of the object and the scene to reveal the information that is hidden from conventional cameras. A standard RGB sensor has 3 channels. Our sensor has 16 channels, and that allows us to decompose the spectrum of the light across our entire imager. This is going to be the smartphone camera of the future. We will not replace the standard camera, but we will be a companion chip to solve the issues with color accuracy and auto white balancing. We see ourselves as a new class of imaging because we have shrunk the known hyperspectral and multispectral technology to a size, a form factor, and cost that is useful for a smartphone and other mobile applications. We have 16 channels. We have SVGA resolution by 860 by 680 pixels, and we cover the visible and near IR spectrum from 400 to 850 nanometer. In comparison with a normal RGB camera and ambient light sensor, we are able to accurately capture the full spectrum information. And what can we then do with it? We can provide 3 times the color accuracy for the smartphone. Not only do we increase the color accuracy of the images in the smartphone, we also solve the issues of auto white balancing in challenging conditions. Here we have compared our solution with the Apple iPhone Pro, but we also have done it with Samsung Galaxy, Google Pixels, and so on. In a challenging situation where the white point is not clearly defined, we change the illumination source from warm white to cold light, and as you can see on the top row, the pictures changes colors quite rapidly. Our solution provides very consistent colors across the situation. But not only is it used for color accuracy, we also use it for beauty and health investigation, food safety, agriculture inspection, security, medical application, and many more. And we want to enable that for any mobile device, including smartphone, but also new mobile devices. So we work with Qualcomm to integrate directly with the Snapdragon platform, and we are working now with other companies to also integrate our data path and drivers with their platform. Our market strategy is to first target the specialty applications to validate our use cases, and thereafter push into the smartphone market to reach high volume business. We are working with every smartphone manufacturer in the world, including some that is not mentioned on this slide. We are also validating our solution with major manufacturers of home appliances, smart cameras, and many other solutions. We have an experienced team across the world taking care of both our technical, go-to-market, and supply chain leadership. What we are looking for is partnerships to validate our use cases in different domains and explore new applications where you can take existing applications of hyperspectral imaging and put it into a mobile application. We want to build our ecosystem by working with new people to engage with our development kit and develop algorithms that can be ported to the smartphone. And finally, we are seeking investment. Our fundraising is ongoing right now. We are raising money to push our product into production. We have a term sheet signed for extended round B, and existing shareholders are committed. To summarize who Spectricity is, we were founded in 2018. We're a deep tech spin-off from EMAG based on 15 years of R&D. We are bringing true color to all mobile devices, targeting a market of 1.3 billion smartphones per year, but starting with niche markets to engage the market. We have raised 28 million euros to date, and the existing investors are committed to the next round. We have 43 employees across the world, with our headquarters being in Belgium, but we have go-to-market team in USA, China, Singapore, Taiwan, and Malaysia. We have our first product ready, and we are reaching the qualification ready to push into mass production by end of the year. And the supply chain has been qualified and is ready to support mass volume. We have a large patent portfolio to protect our technology, and I hope this brings the conclusion of who Spectricity is, and hopefully you will reach out to us and learn more about our company. Thank you.
Thank you, Henrik, from Spectricity. Perfect job, just in time.
Okay.
I could allow one question. Jury members, is there a question you would like to ask Spectricity?
Great presentation, really well done. The only aspect we haven't really touched on, maybe because of time, is that technology. So, fortunately or unfortunately, I come from the CMOS image sensor world, and I know how challenging it is to put, RGB filters on a sensor. Now you're putting 16 of those, right? So, how do you guys do that?
So, we work with existing commercially available CMOS imaging sensors, and we apply our patented filter layers on top. It's publicly known we work with X-FAB in Malaysia, and we have taken the technology developed at IMEC and transferred it to the fab in Malaysia. We do thin film filters in the deposition, and of course the detailed technology I cannot share with you here, but we have developed a technique that allows us to scale to additional filters in a very cost-effective way. So we have specific patents to protect our technology there, and the whole point was we can do this in a cost-effective way so we can target this market. Yeah.
Thank you. So Henrik from Spectricity, thank you for your pitch.
Thank you.
My next speaker, a warm welcome to Maximilian from Medapspi.
Yeah.
And you are going to talk about machine vision redefined, the power of digital twins and synthetic images.
Yes.
Sorry, digital twins and synthetic images, and
Very
it's
good.
a very hot topic. So the floor is yours.
Okay, thank you. Perfect. So I'm Maximilian Grau, and machine vision is rising. Every time, more and more machine vision is used in automation systems. But if you ask your colleagues, then they always say, machine vision often finishes as last in an automation project. And there are many reasons. In a machine vision project, first you have to rent the components, and you have to make looking which components do you need, which camera system, which illumination system. Then you make a feasibility study. It means you need first the physical part to look which components you need. This takes time. And after them, you can start to program your imaging processing software. The next problem is, if you want to test your inspection system, you need the real assembly line. So you have to wait until the mechanical and electrical engineering are ready with your work, with this work. Then you can finish it. So this is the reason why machine vision always comes at last in an automation project. So we are the startup Medapsi from Dingolfing, and we want to change the game. We want to make it able that everyone can solve the machine vision challenge before you have the hardware. This is one of the craziest and most difficult ideas you can have in machine vision, but it's one of the most promising thing what you can have in machine vision. And we are doing this with what's called digital twins. So here you see on the left side our software platform, our web browser platform, and it works like this. In our platform, you upload a 3D model of your target, and then you choose a material. After then, with our database, you can choose the right components. We have all cameras, all lenses, and all illumination you have on the market. You set up in the system, in the scene, and then you get in minutes a synthetic, realistic image, like this one. And this whole process takes only some minutes. Here, with this case, you save a lot of time of the whole project. Why? Because a lot of steps you can do it digitalized and not in real. And of course you can put some task in for. So here another examples. The benefits of digital twins are you can change everything. You can change light, position, materials, or the last one is the most interesting stuff. You can add defects. So if you have synthetic images with defects, you can look how to program your imaging processing software. So it means you can solve it before the errors happens. And this saves a lot of time and money. Here's one customer of us with the proof of concept. Thank you to B&R that we can show this project. We did a digital twin of the system, and with their components, we put the stuff in the right position, and then we did the synthetic images. Now you can compare it side by side with the real image. Looks really realistic. So generally, what can you do with digital twin? You can choose the best strategy, how to solve the machine vision challenge. You can save time. And it's also a really good tool for sales. It's not for engineers, also for sales to convince the customers, which components they need. The second big use case is we can also generate not only one image, you can generate unlimited image, 1,000 or 10,000 images, which are also automatic labeled, pre-labeled. This is not manual labeled. This is with our platform label. And with this training data set, you can train your AI for it. And we also generate metadata from each image, which can you also provide to your AI. Here also some examples what we can change. We can change the color if you have many parts, or we're doing binary images. And this, of course, save also time. And the one big benefit is if you are missing data, if you have a lack of data, you can fill it with synthetic images instead of real data. So you have a bigger balance of the data. So what are we offering? We are offering three stuff. As a first, as a service, if someone needs a training data set or want to see a digital twin, we can offer, we can do it for a specific project, but our main business are license. We are offering 1 year license where the customers can get access to our platform to generate their own digital twins and synthetic images. And then, with the feedback of the market, we built another business model, the white label solution. Because a lot of components manufacturers want to add this platform in their website to accelerate their sales. So you have a white label solution with only your components. So there are many benefits, many stuff you can do with digital twins and synthetic images. Our goal is, of course, solve your machine vision challenge before the hardware. But three things you should remember. First, show 1 million inspection system with only one laptop. Second, generate synthetic pre-labeled data in just minutes instead of hours or weeks. And the third one, accelerate your sales with simulation and convince the customer. We have our booth here. You can see our platform, also our simulation expert is here, have a talk. And yeah, for the next machine vision project, if someone asks you, what is the status of machine vision? You can say, we have already done. Thank you.
Wow, perfect timing. One quick question, but a quick question. Mark, our chairman.
Hi there. That's great. The question I've got is, how do you create the digital twin of the camera or the light profile? Because that has to have a specification that is unique to that product. And how do you create a digital and how long does it take to create the digital twin? Because you need, in theory, every product that's out there that's here in this show to have a digital twin, and that must be a very time-consuming task.
And an accompanying question from pretty close to that. How close is virtuality and reality?
What is the...
How close is virtual and physical world? I mean, you have a digital twin.
Yeah.
And if you did it physically, you may have still a little gap there.
Yeah.
So how close is that to reality?
Okay, now I have it's from my question. Okay, the first question I want to answer. Yeah, so at the moment for the customer project, what we have, it's enough with the technical sheets. What is the most components manufacturing is offering? We're taking this data, for example, the pixel size and pixel width and everything, and then we put on the on our platform. At the moment we're doing manually, but in the future we have to look to how to automate it because there's a lot of components in the market. But at the moment this is enough. And the second question, yeah, this is a really tough question because there's no algorithm or mathematical form to measure the quality of what is reality and what is synthetic images. This is the reason why we show always what is a real image, what is a synthetic, so we have an opinion, but this is something that is at the moment there's also no research or something. Also we can't get at the moment a number, but for example, the slide with the range I showed to to a lot of people, and I asked them, hey, what is the real image? And 60% said the wrong image is the real image. So they're really close.
Thank you, Maximilian. Also, high interest in Medepsi.
Thank you.
My next speaker, PXE holographic imaging.
Right.
Jan Nier is already with me. The floor is yours.
Thank you very much. Hello, everybody. Thank you very much for joining this session. My name is Yanir Heinik, and I'm the co-founder and CTO of PXE Holographic Imaging. It's a pleasure to present PXE to you today. I'll start by exploring the evolution of imaging technology, which has undeniably become an integral part of our daily lives, from taking images on your smartphone through automotive applications, home applications, industry applications. Imaging systems are everywhere. The rapid advancements and widespread adoption of cameras have really transformed the machine vision market, shaping it into the industry that we see today. Despite accomplishments in miniaturization, in ease of integration, in cost reduction, the core physics of cameras have remained virtually the same since the era of film photography. 2D cameras treat light as rays, advancing in straight lines and being focused on a light-sensitive plane, either a chemical film or a photodiode array, to produce two-dimensional images, either in color or monochrome. But that's about to change. Sorry, a small blackout. That's about to change. Pixie's groundbreaking innovation unlocks a new era in digital imaging. Our invention can transform 2D cameras into advanced imaging devices capable of delivering both high-quality color images together with accurate and detailed depth maps. Now let's dive and take a closer look into our technology. Pixie aims at exposing light's wave-like nature. Those waves of light contain information about the color of the source and the distance to it. A Pixie camera looks just like a 2D camera, only instead of focusing light on a color filter array that is common to most RGB cameras, we focus light on a holocoder that is placed on the raw CMOS sensors. Now, this holocoder is a Pixie-designed diffractive optics element. So the raw sensor underneath now records diffraction patterns which encode within them both the color information and the depth information. Then Pixie algorithms analyze these diffraction patterns both deterministically and efficiently, and output the RGB image as well as an IR image and the depth map. So how can this revolutionize the machine vision market? So to answer that, we need to revisit traditional technologies that you treat light as rays and use a color filter array to produce color images. So although these technologies really were the foundation of imaging for decades, they have some inherent limitations to them. For example, imaging in low light conditions, or the absence of depth information, physical depth information in the image. Now, these limitations really impair the ability of 2D cameras to perform complex machine vision tasks like 3D SLAM or object detection and or 3D modeling, etc. Now, naturally, over the years, advancements have been made to overcome some of these limitations. For example, stereo cameras, as well as structured light or time-of-flight devices, can add valuable depth information, but they have limitations too. For example, imaging reflective surfaces or under ambient light conditions, but above anything else, they really add to the overall complexity and cost of the system. So the only way to truly revolutionize the field is to eliminate its trade-offs, and this is what Pixie actually does. So I want you to meet Erez, our system engineer, and Charlie, the office dog. They are the heroes of this medium-range demonstration movie. Both the RGB image and the depth map come from the same Pixie camera. This is how we filmed this movie. This is a key feature of our technology. All the information channels are completely fused and synchronized because they come from the same captured data. Oh, in the next demonstration I'm going to show you of this short-range packing application, although the 2D image is of high quality, you can't really tell if either of the cans are of different height, and the depth image that is again natively fused with the 2D image reveals the truth. Two of the cans are of different height. The difference is of 2 millimeters, a few millimeters in this example. Pixie offers a groundbreaking solution for perception, delivering both high-quality depth information together with RGB images on a single sensor from a single snapshot. We are completely agnostic to the underlying sensor or the lens design, making us relevant for any application and any use case. And we are a true drop-in replacement to any existing workflows. I want to thank you very much for listening and invite you to come visit our booth. We have a demo to show you there, and we'd love to see you. Thank you very much.
Thank you, Janir from Pixie. Great. For fairness, one question. Martin, a quick question, please.
Thanks for your talk. Which type of processor you need for post-processing the data?
Okay, that's a good question. As I mentioned, the algorithms are deterministic, not only on the physical sense, they're deterministic also on the processing pipeline sense. So we can actually calculate the amount of operations that are needed for decoding an image, and the magic number is between 100 and 200 operations per raw pixel. Now, how this translates to gigaflops and power consumption and such depends on the sensor resolution and the platform that you're using, but this is Pixie's magic number.
Thank you, Janir. Last speaker for today, Luigi from Questa AI. He's talking about advanced visual inspection, deep learning, and neuromorphic vision. Luigi, the floor is yours. You just, yes.
Okay, thank you very much for this opportunity. Today I will tell you a little bit about our activities in connection with software for machine vision, and in particularly the use of neuromorphic cameras in application of quality control. So let me start a little bit about telling who we are. We are a young startup. We've been founded 3 years ago. Both me and my co-founder, Ricardo, comes from a background in research, and several people in our team come from that background too. So what we do is that we have a need to integrate solutions coming from research papers to develop a new prototype. Within our competencies, we have typical libraries for quality control that I'm sure you are aware about, for object detection, beam packing, anomaly detection, QR, and data matrix. But today I want to talk to you about other things that we are doing, and in particular our research focus on the integration of cameras with the neuromorphic sensor with images coming from traditional frame-based camera. So for those who do not know, neuromorphic sensors are a new paradigm, a different paradigm in computer vision, where basically what the sensor captures are changes in the activation of the pixel, and so we have basically typically a sparse set of events which can be activating or deactivating for a given threshold. So we have a sparse representation which differs from the typical dense representation of a frame, but also we have advantages. We have a very high frequency because the timestamp of the event is at the level typically of the microsecond, and we have a huge dynamic range which is comparable to the one of the human eye, which allows to be able to capture information in scene which may have a very high contrast, and so we do not have to worry about dark corners or very high contrast scene, and so this provides advantages in application where you do not have control on the lighting, for example, or where such control is very expensive, for example, in welding. So when you wanted to use this type of data in your algorithms to extract information and to extract a high-level inference, of course, you have the issue that typically deep learning algorithms that you may use for typical frame-based images do not work very well in this context because they are not able to exploit the sparse representation of the events, which is an advantage of such representation. On the other side, when you use this type of camera, if the object is not moving, you do not see the object, and so you need to memorize previous information from the past, and you do not have all the rich features that you may have from a frame-based camera. For example, you do not see colors with typical sensor, and you typically have a low resolution, and so on. So what we are doing is to integrate the information coming from both using a stereo system. The two cameras are synchronized, and so we have the possibility, synchronized in time and space through the stereo calibration. And so we have the possibility to combine both paradigms and extract different type of features, some coming from the traditional camera, some coming from the event-based camera, and use them at different time resolution depending on the specific process that we want to analyze. So a new feature that come easily and they are very interesting from event-based camera can be, for example, vibration, because we have a way to understand if a pixel is vibrating at a frequency which is typically much higher than the one of the frame per second of a camera. We can easily detect instantaneous velocity. We have sharp edges also in the presence of a low light condition. Then on top of that, we can introduce and use and exploit all the standard frame-based features that you may extract, and we can combine them through a proper alignment of the images, typically working at a different frequency, high frequency for the events and a little bit lower frequency for the frame-based. The application of interest for us are high-speed tracking and anomaly detection, particularly in manufacturing processes. So unfortunately, my presentation is not very friendly in terms of video, and if you want to see the videos that we have, and they're very interesting, you have to come to the booth, which is over there in the startup area. Here we can see, basically, I can tell you, it is a tracking application in which the one on the right are bubbles coming from generator of oxygen and bubbles in an aquarium. So the speed is very, very high. And you will see that even if we go, I think, at 200 frames per second on the right, we see that there is a gap between the movement of the bubble, while the video will show you that we have a continuous movement that allows us to track the object, count the object, see the movement, and characterize the process. This is, of course, an example and application. 2025 is what we are working on. Well, we are working in integrating this sensor in a unique smart camera, which would allow us to run application on the edge. Our technologies are based on the sensor of Prophecy that we are integrated through the platform of Framos. And our vertical of interest are, as I told you, high-speed tracking, anomaly detection. And we are very interested in understanding how much we can push of our design algorithm on FPGA to even further speed up the processing, which is critical for this type of application. OK, this concludes my presentation. Thank you for your attention. Please come to visit at our booth if you have more questions. And if not, you can also ask me here, and we'll be very happy.
Thank you, Luigi.
Thank you.
From Questa AI. Is there a question from the jury members? Everything answered. So thank you, Luigi.
Thank you.
And also thank you to Henrik, to Maximilian, and to Janir and Luigi. Great first session. Let's wait and see who is going to win. I already shared the voting link with you in the calendar and via email, so let's wait and see. And if you have 2 minutes time, we'll announce the winner here. have 2 winners.
That's right.
So you're going to have to share the champagne. So, Maximilian, Dafür, Pixie, and
Thanks.
Okay.
Er was auch sehr gut.
Thank you.
Good pitch.
Is it working?
Very much.
Can you hear me? Okay, so we have 2 winners. Congratulations to Maximilian and to Janir, Medapsi and Pixie.
Appreciate it.
So,
Yes, you kind of have to share.
We're going to have fun tonight indeed.
Yeah, of course. Yeah, with this bottle. Woo.
So, well deserved, the both of you. We're going to bring another bottle of champagne to the booth. No worries,
perfect.
Okay, so no sharing.
Okay.
You can have this one.
so thank you. And it was a very tough race. So
So now everyone.
Maybe we can step one step forward. So
Sure.
you can take,
Sure. Oh,
well done.
thank you very much.
Okay, thank you.